Hi, everybody, and welcome to Echo Live, coming to you from the Michigan Science Center's Distance Learning program. Now, this is our first program being casted to you from my own house, so welcome. Thank you guys for having me in your home as I do some science from my home. Today, we'll be doing some at-home chemistry. Now, throughout Echo Live, we've done a lot of do not try this at home science, which is really fun. I get to show off some of my biggest and best science experiments, which are way too dangerous and should never be tried at home. But today I thought it would be fun for us to show off some activities that you can and you should try at your house using materials that you might already have. Now, all the experiments I have to show you today, if you don't have these materials at home, you could probably pretty easily purchase these on your next necessary run to the grocery store. And we'll be posting activity guides for each of the lessons that we go over today on the Michigan Science Center's Facebook. We'll be posting a link to our webpage, and that webpage is just our website, and you search for At Home Science. So we'll be posting that link during this program, and then that is where you can find the activity guide for all of these at-home science experiments. Today we'll be focusing on chemistry, and we've talked a lot about chemistry so far in most of our Echo Live programs. So a brief recap about chemistry. If you happen to remember what chemistry is the study of, go ahead and type that in the chat feature now. If you don't know the answer, still go ahead and use the chat feature for us, because that's how I'll be able to communicate with you throughout our Echo Live program. Now type in the chat, tell me if you remember what is chemistry the study of. If you don't remember that, you can just go ahead and say hello in the chat feature for us. Let us know where you're watching from and maybe what grade you're in as well. Now I'm seeing some answers rolling in for what is chemistry the study of. It is certainly the study of science, some sort of science, but more specifically, it is the study of matter. We've talked a lot about our states of matter throughout Echo Live so far. So a brief recap on our three main states of matter that we experience here on Earth, which are our solids, liquids, and gases. We've manipulated our states of matter mostly through temperature, or by adding and taking away kinetic energy. So even though the molecules in this diagram, which are those small blue dots we see in our three states of matter, even though in this photo they're not moving, atoms and molecules are always moving around. All atoms and molecules have energy, and they have different amounts of energy, sometimes depending on the state of matter they exist in. If we think about our solids, we can see that those atoms and molecules are packed very closely together. They're not moving around very much, and they don't take up very much space. If we add kinetic energy, which we can observe as heat, we can actually melt that ice cube into liquid water. Now we see those atoms and molecules are a bit more spread out, and they're actually able to flow. So if we think of water, it's not necessarily as rigid as a solid, but we can still hold it in a container and keep it in one space. However, if we add even more kinetic energy in the form of heat, we'll cause that liquid water to evaporate, and it will turn into a gas. We experience water as a gas here on Earth all the time, and those molecules in this gaseous water are actually very spread out. They can't be contained, or they don't want to be contained. They want to keep expanding to fill their container and then even further. And so those molecules have a lot of energy. They'd be moving very quickly if we could actually see these molecules moving around. We know that if we remember back to our Echo Live segment talking about frostology, or making things cold, that we can actually reverse this process. So if we take away kinetic energy or heat, we can turn a gas back into a liquid back into a solid, and this cycle can just keep going round and around and around in either direction, really. Now that is talking about how our molecules move. An experiment that you can try at home to understand the expansion of gases as we create them is by creating something that we like to call Alka-Seltzer Rockets. So for this experiment, you'll only need a few household materials. The main things you'll need for this reaction are Alka-Seltzer and water. Alka-Seltzer and water, if you're familiar with this, if you've ever dropped an Alka-Seltzer tablet in water before, we know that it starts to fizz. what we're seeing is actually that Alka-Seltzer creating a gas. So it's pretty easy to see this reaction. And we might also know that that gas is expanding. If you want to create a safe explosion, unlike some of our explosions we've done so far, if you'd like to create a safe explosion at home, all we need to do is trap that expanding gas inside a closed container. We'll be using film canisters for this experiment, which are these small plastic tubes that have a snap-on lid. If you know an adult in your life, you should ask them if they have any spare film canisters laying around that they no longer use. Not very common to use film for taking photos anymore since we live in the age of digital cameras and cell phone cameras. But if you know someone who might have some film canisters laying around, I'm willing to guess they might donate them to your science experiment. So what we'll be doing is we'll be creating our explosion inside that film canister. It's a pretty small container, so it doesn't take very much of our Alka-Seltzer and water in order to create this reaction. We'll zoom in on the table. You can get a little bit closer look at some of our materials here. Now for this, we'll only need to fill our Alka-Seltzer and water about halfway up the film canister. Since we'll be launching a rocket, there is one safety precaution that I'll need to take while we do this experiment, which is wearing a pair of safety glasses. If you don't have safety glasses at home, sunglasses will work just fine for this experiment. I would highly recommend you do it outside, since this will create a little bit of a mess, and it's great to get fresh air right now. But this reaction should either be done outside, wearing your safety goggles no matter what, or on a tray if you are doing this inside. Now, I'll get to another note about this once we see our first reaction go off. So we'll zoom back in on the table, and I'll pour just a little bit of water into each of our film canisters. I'm filling them about halfway full with just regular water from the sink. Now, in each reaction, I'll be using about 1/2 of a tablet of Alka-Seltzer. And we said that as soon as this stuff hits the water, it's going to start to create a gas or generate pressure. Because that gas is expanding, right? We'll trap that air pressure inside the canister, which will create thrust for our reaction. This works best if you seal your lid and then flip your film canister upside down. Now, it's really difficult to know exactly when this film canister explosion is going to go off. I can see here that the pressure is starting to build. The film canister is starting to swell as the gas inside starts to take up more and more space. You don't lean over the top to go to completion on its own. Now we'll start our next one here, since we know we'll have about a minute or so before that one goes off as well. So this is a reaction that you can try at home. Now, here in my house, I've made sure that I've positioned my Alka-Seltzer Rockets so they are not underneath a light fixture. Again, this would be best performed outside, where you can get some fresh air and have no worries about making a mess once this explosion goes off. But our reaction here is not underneath a light fixture, just in case once our rocket goes off, which is pretty loud and pretty exciting, just to make sure it doesn't hit any of those light bulbs that might be above our reaction. Now, if you don't have a film canister at home, or you don't know someone who might donate you some film canisters, I get that question a lot. What could you use instead? Now, it's important that for this reaction, that you use some sort of container that has a press-on lid, because we're really relying on that expansion of gases to pop the lid just using pressure, air pressure. So it can't be a screw-on lid, so a water bottle would not work. A suggestion I have is that if you can find any other sort of small Tupperware container, or maybe a portion cup or a condiment cup with a press-on lid, you could try using different types of plastic containers for your experiment. You don't want to use anything made of glass, because you do see that it did really shoot up towards the ceiling and fall back down, so nothing glass. Always use plastic. And then always remember, though, that if you are using a larger container, you might need to use more rocket fuel or Alka-Seltzer and water in order to launch your rocket. So that is talking about our states of matter and how they change using a chemical reaction, or as they start to take up more space. Now, we'd also like to talk a little bit about the periodic table, which I have behind me. Now, we arrange things on the periodic table in a really specific order. Atom number one, or number one on the periodic table, is what we call hydrogen. Hydrogen is very important in chemistry because it's one of the main building blocks of life. Now, it's important in a lot of chemical reactions as well, and we'll be actually measuring the amount of hydrogen in each of the solutions that I have here on the table by doing a pH test. If you know someone who has a pool or who might be testing the pH of a pool, right? We usually use these little dipsticks that change different colors based on the pH of the pool. Now, we might be familiar with pH, but we might not necessarily understand what it means. But pH is basically measuring the amount of hydrogen in a given solution. If a solution has a lot of hydrogen in it, that means that it is very acidic. If it has a high concentration of hydrogen, we call those things acidic. So if we remember our pH scale, which we talked a little bit about during our colorful chemistry episode, we can remember that our acids actually turned red on our pH scale. So this is a pH scale using something called universal indicator, which is what I have here on the table today. But there are a lot of different pH indicators that you don't need to purchase from an industry supply source or from a science supply company. A lot of vegetables or produce actually have natural pH indicators inside them. So if you've ever heard of something called red cabbage, I have a photo of it that I can share with you. This is chopped up red cabbage. You can find it in almost any grocery store. And this actually has an ingredient in it called anthocyanin. Anthocyanin is a natural pH indicator, so if it's mixed with different solutions, you can create different kinds of reactions, and you'll get a different color change based on its pH. So this is a low pH or an acid, which turn kind of towards that red or pink side of the scale, just like our universal indicator. And then turning towards these blues and greens would be bases. So people are pretty familiar with acids. If you're familiar with acids, and maybe you know that acids can be quite dangerous, tell me in the chat feature, what is an example of an acid? Something you might know of. Think of strong acids, think of maybe weaker acids. What do you know is acidic? Go ahead and tell me in the chat feature. So if you remember back to our colorful chemistry episode, or episode 1 of Echo Live, we created an acid called carbonic acid by dissolving dry ice in water. Carbonic acid is the same acid that you would find in soda, which is what makes it corrosive to your teeth. So that's an example of an acid, but not necessarily a strong acid, since it is something that we ingest and put inside our body. I see some great answers here. I see guesses for orange juice, lemons, tomatoes. These are great answers. Vinegar. So generally, acids taste pretty acidic or taste sour. So if you think of any citrus fruit, those all have citric acid inside them. And so things like oranges, lemons, and even vinegar are all examples of acids. So we have an experiment that we can do right here on the table, which is using our universal indicator in order to test the pH of some household substances. We'll be posting an activity guide later today at our website /@home-science, where you can actually use red cabbage to test these same things. So we'll zoom down on the table here, and you can see that right now, our universal indicator is this nice kind of dark green color. Might look a little blue, but I assure you from at least where I'm standing, this is our neutral zone. So we know that acids will turn red, bases will turn blue or purple, and then somewhere in the middle we have our greens, which is what our universal indicator should look like when it's just dissolved in water. We'll be leaving the center beaker alone. We won't add any ingredients to that beaker so that we can use it as a control. So we know that we're looking for the difference between our control and any of our other beakers. Now, a lot of you mentioned lemon juice, so I have some lemon juice here that we can use for testing. And we'll go ahead and put just a few drops of lemon juice inside that container and then give it a stir. Amazingly, it turns bright red. You guys already told me that lemon juice is acidic. A good way of knowing this when it comes to foods is that if it tastes sour, it is acidic. And lemon juice is one of those really, really sour foods. Now I also have some vinegar. This is distilled white vinegar, so there'll be no color change from the color of the vinegar itself. And then we'll just go ahead and mix that in to our next beaker. You already told me that vinegar is also an acid. Now, vinegar doesn't taste very good, but it is one of those very, very sour substances. And you can see that while lemon juice is pretty bright red, we have a little bit less red, so maybe a little bit less acidic with the vinegar. And the next substance we'll be testing is something called Alka-Seltzer, which you might remember from our first at-home science experiment that we did with the rockets. Now, Alka-Seltzer, we said, generates a gas as it dissolves in water. The main ingredients of Alka-Seltzer are citric acid, which we just said we find in lemons, but also baking soda, which is a base. So let's see ultimately what kind of reaction we get when we dissolve our Alka-Seltzer in water. We get a nice orange change. So even less acidic than our lemon juice or our vinegar, but the ultimate product of this Alka-Seltzer in water reaction is an acidic solution. So we'll leave that one right there. The very last one we'll be testing is Windex. Now, definitely don't recommend drinking Windex since it is a cleaner. That would be highly dangerous, but we'll be adding some Windex into our last container. Now, important to note is this solution is blue. But it's a very bright, very light blue. So let's see what kind of change we get when we introduce this to the universal indicator. That turns a nice dark purple, much darker than the original blue. So we know that the color change is not necessarily from the color of the Windex, but it is because of its pH. This solution has the lowest concentration of hydrogen ions, which gives us a pretty purple solution. Now, if purple's your favorite color, like I know it's some people, this is a great reaction to try at home. Now, you'll notice that in a couple of these beakers, I had some pipettes that I used for stirring. One important thing that you'll need to remember if you try this experiment at home is that you should never move your pipette or whatever device you're using for stirring between your solutions. You definitely don't want to have any cross reaction, and you don't want to contaminate your substances. And so you'll always want to make sure you use a different device for stirring for each solution, or make sure you wash it off really well, wash and rinse between mixing. So that is pH testing. And again, we'll be posting a lesson that you guys can try at home using red cabbage. And I did see a really great question about how is red cabbage different from green cabbage? Now, even though they taste pretty similar, the main difference between them is that ingredient anthocyanin. Anthocyanin is what gives red cabbage its purple color. And that ingredient or that chemical is actually what reacts with different substances to get a color change. So green cabbage does not have anthocyanin in it, and so you can't use it for pH testing. It's still pretty delicious. Now, our last set of at-home science experiments is using baking soda and vinegar. So we use vinegar and we know that it is acidic, and we mentioned that baking soda is another of those ingredients in Alka-Seltzer. When we mix baking soda and vinegar together, we actually get an acid-base reaction. So we'll find out what happens when we safely combine an acid with a base. So I have this reaction set up over on the other side of the table. And I've got my vinegar in this cup and my baking soda down here in the other. Now, you might be familiar with this reaction. You might know what might happen when I mix these two things together. It's pretty similar to our Alka-Seltzer reaction. We know that we're pretty familiar with how this looks, but I'd also like to have you guys make some observations about when you try this at home in terms of some other things that might happen. So right now, just for the sake of observing this reaction, if you've never seen this one before, I'll just pour our vinegar down inside our baking soda. And we get a really cool, really fizzing reaction, almost like our Alka-Seltzer reaction, but even bigger. So when those acids and bases mix together, they generate a huge amount of gas, which we see in the form of these bubbles. So you might know what this reaction looks like, but we might not necessarily know what this reaction feels like. For this, we're combining two common household substances, two things that are safe and don't give us a very dangerous reaction. So what I want you to try at home is combining these two ingredients in a container where you can actually feel the effects of this reaction. I'm going to try putting both of our ingredients, our baking soda and our vinegar, inside this plastic bag. So we've got about just 1 spoonful of baking soda. And we'll be mixing in just another small amount. I have about 25 milliliters of that distilled white vinegar. And then as soon as I dump it in, I'm going to seal the Ziploc bag. Now the bag is starting to expand. If I zoom back down on it, the bag is starting to fill with gas. And so even though I squeezed most of the air out, now this bag is really full of that gas that was created when this acid-base reaction happened. But if I shake the two ingredients together, I can actually feel something very, very interesting happening. So this is one that you'll have to try at home if you'd like to feel the results. But basically, we've created an endothermic reaction. Now, we talked about chemical reactions already this week, that they're different from physical changes, that we're actually creating something new, which means that in a chemical reaction, we actually have to make and break chemical bonds, which means that there's an exchange of energy somewhere inside this system. For this, we are calling it an endothermic reaction. Endothermic reactions, by rule, actually feel very cold to the touch. So this reaction, when I shook up the bag, actually feels extremely cold, almost like one of those ice packs that you crack and feel the reaction. That's another example of an endothermic chemical reaction happening. So in endothermic reactions, they actually absorb heat from their environment. So when these reactions go to completion, sometimes they need a bit more energy. And so they'll actually absorb it from your hands, from the air, which makes them appear to feel cold as they absorb that kinetic energy. But there are other kinds of reactions as well. So if we have endothermic reactions which feel cold, we must have exothermic reactions as well, which feel hot. So exothermic reactions, as they're making and breaking bonds, they'll actually release heat into the environment. Our combustion reactions that we've done earlier on Echo Live, those are examples of exothermic reactions. But since fire is extremely dangerous, that is not a reaction that you should try to recreate at home. If you'd like to recreate a safe exothermic reaction, you can follow the same procedure for our baking soda and vinegar bag, but using water and road salt. So we're about done with road salt for the year, hopefully. Hopefully we don't get any more snow here in Michigan. But if you do have some road salt left over, you can actually dissolve that in water inside the Ziploc bag, shake them up, and you'll actually feel heat. So that would be an exothermic reaction. So again, these reactions are all being posted on the Michigan Science Center's or on our At Home Science website page. We'll be posting a link to that with this video as soon as it ends. We'll be posting all of our at-home science experiments that you should try at home there. Now, we're also going to be posting an at-home guide to an experiment that we've already done, which is our elephant toothpaste reaction. So we'll be doing elephant toothpaste one more time, diving into the science, but we'll be explaining how you can safely recreate elephant toothpaste at home using regular food strength or hydrogen peroxide. Now is a great time to pause for any questions that you might have at home. If you have any questions about the experiments we've done, or you'd like to, let's see here, if you have any questions about what we've done so far, or questions about elephant toothpaste as it's about to come up, go ahead and type those in the chat now. We'll get around to answering those in just a second as they come in. Also going to take this time to make sure that we, as always, thank the sponsors of the Michigan Science Center. Our sponsors, like the DTE Energy Foundation, are the reason that we can provide these Echo Live programs to you guys at home every weekday at 2:30 p.m. Eastern. We really love providing these programs, and I'd love to keep doing at-home science with you guys, but we can only do it thanks to people like DTE. So let's take a look for questions. See, one great question that says, why is it that calcium chloride or our road salt melts snow? And that's simply because it is an exothermic reaction. As that substance, that road salt, dissolves in water, it creates an amount of heat, which if it's next to something like frozen water, ice, that heat will cause the ice to melt. And so that exothermic reaction is actually why we use it to melt the snow on the ground. Why is water H2O? So water is just the common name for the substance H2O, but we call it that because H stands for hydrogen and O stands for oxygen. So that means that there must be 2 hydrogens and 1 oxygen atom in every molecule of water. Great question. Can you drink the things? That is a great question. Since we are doing chemistry, you'll notice that we're taking some safety precautions. And the #1 rule of chemistry is that we never, ever eat or drink anything inside the lab. It's not necessarily that anything we're working with is hazardous. You know, most of the things we've worked with so far today are things that are food safe or were at one time, maybe aside from the Windex, but that doesn't mean we would ever want to eat or drink anything that was a part of a science experiment. Again, that comes back to that process of contamination. So if you think about, you know, things that might have touched each other on this tray, you know, what if some Windex did happen to get inside one of my other containers that was holding something like the lemon juice? Never ever want to eat or drink anything while you're doing science. Save that for later. Make sure everything's cleaned up and nothing is contaminated. What is hydrogen peroxide? That is a great question. So hydrogen peroxide has the chemical formula H2O2, which sounds really similar to water. So water is H2O, meaning 2 hydrogen, 1 oxygen. H2O2, or hydrogen peroxide, has 2 hydrogen, 2 oxygen, and that substance is actually highly unstable. The hydrogen peroxide that you have at your house is regular strength, very inexpensive, but still very difficult to make. Regular strength hydrogen peroxide is about 2% hydrogen peroxide, the rest of it is water. Now, hydrogen peroxide is really unstable. It really wants to become water again. It wants to kick off that extra O or oxygen atom and return to the state of being water and oxygen gas. That process happens when any sort of energy is added into the system. So even with hydrogen peroxide sitting out in the light is enough to start breaking down hydrogen peroxide back into water. It happens pretty slowly. And so it's not very exciting to watch, but which is why we do our elephant toothpaste reaction. That's also why hydrogen peroxide is sold in brown bottles. So bottles like this contain our hydrogen peroxide, and that's actually to keep light out of the bottle, slow that reaction down and stop it from happening so fast. Now, our version of elephant toothpaste that we're doing here is using some pretty strong stuff, really strong. So I actually need to grab a pair of safety gloves. Because this stuff, instead of being about 2% hydrogen peroxide in the rest water, this stuff is about 30% hydrogen peroxide. Same chemical makeup, still H2O2, that will be breaking back down into water and oxygen gas, just in a much higher concentration. If you'd like to try elephant toothpaste at home, unfortunately, you can't buy this strong lab grade stuff. It's very, very dangerous. I would never recommend that you try this exact version at home, but using regular strength hydrogen peroxide, you can recreate this exact same ingredient. The only thing you'll need is regular strength hydrogen peroxide, some food coloring, a little bit of dish soap, and a small amount of a catalyst. Now, our catalyst for my reaction is potassium iodide, which we keep in another brown bottle. It's basically just a salt. I'm going to turn off my virtual background here, just in case it's interfering. But if you were to recreate this experiment at home, you would want to use yeast. Yeast is found at almost every grocery store, and it also acts as a catalyst for hydrogen peroxide, breaking back down into water and oxygen gas. Now, if you remember our elephant toothpaste reaction from colorful chemistry, you know that our food coloring is not involved in the reaction. It's not actually changing anything. We don't see anything happening in the beaker as we add food coloring since it is water-based. Our dish soap, same thing, not reactive with our reaction at all, but it is going to help us to trap those oxygen bubbles or oxygen molecules as they're released from our hydrogen peroxide. Now, I've already poured just a small amount inside before the program, and we'll go ahead and we'll add in our catalyst which is our potassium iodide, but again, at home, you'd be using a yeast solution, and this will all be posted on our website later today. We'll go ahead with this reaction in 3, 2, 1. And this is, again, an exothermic reaction. If you look closely, this is letting off a huge amount of heat. You might be able to see steam. If you can't see it at home, I will tell you that it feels very warm, and you'll get to experience this at home, even using the at-home version of elephant toothpaste with the 2% hydrogen peroxide. This was one of those exothermic reactions. It released heat as those bonds were formed and broken. And so this brings us back to that diagram of our exothermic and endothermic reactions. Now, I'll stick around for about, let's see if we have any final questions before we go. If not, we hope that you guys will continue joining us for Echo Live. We'll be doing more at-home science with you on Echo Live every weekday at 2:30 p.m. Eastern. I see some comments that it looks like soda bubbles. It does look a lot like some of our other reactions. So we've done a lot of bubbling chemistry, which really just brings us back to that first diagram, right? Even if we're talking about pH or we're talking about acid-base reactions, right? Keeping in mind our states of matter is really important to everything we've tried. If we're making or creating gases, if we're rearranging molecules or not, right? That all comes back to our states of matter. Thank you, Raul Roscoe. This is a cool studio. I'm coming to you live actually from my basement. So we'll be doing some more do not try this at home science as we keep going with Echo Live. But we'll also be adding some try this at home science into the mix too, because we want you, everyone at home, to be able to try some of these experiments. Make sure you tag the Michigan Science Center if you get any sort of cool results from your experiment. Make sure you tag us either on Facebook or Instagram, or send us an email with any pictures or questions that you might have. We are so excited that you have some of these experiments that you'll now be able to try at home too. What are examples of yeast type catalysts to use at home? So really just active yeast, we dissolve it in warm water. That is actually a really great catalyst all on its own. If it's inactive yeast, so if it's already been baked, it doesn't work quite as well. So grinding up foods that have yeast in it don't work for this reaction necessarily, but that active yeast, that ingredient, will work really well. Thank you guys so much for joining. We'll keep seeing you guys at 2:30 p.m. Eastern every day for Echo Live. We're so excited to keep bringing you science experiments. If you enjoyed this one, make sure you share this video on your Facebook page so that others will join as well. Thank you so much for joining. We really hope to see you again tomorrow and pretty soon after that. Bye.